Welcome everybody to another session of Lógicos in Quarentena. On behalf of the Brazilian Logic Society and of the Logic Interest Group of the Brazilian Computer Society, I'd like to introduce Professor Yves Beziau, who accepted to give this talk. Yves, thank you very much.
Thank you very much for the invitation, and I would like to say that it's very good. This seminar of the Brazilian Logical Society is very good. There are many talks. I mean, it's one of the, if we can say, it's one of the few in the world to a country where there is a webinar, as we say, webinar of logic every week, and many different interesting talks, many interesting speakers. So I'm glad to speak here. So I would like to know if everybody is listen to me good, if the sound is good, and if the slides are good. Everything is okay?
Yep.
Okay. So let's go. So as I was explaining, this talk is about a paper which was already published, and I will say a few words about this paper to start with. In fact, this information I will give now, it's at the end of the paper, so it's a reverse presentation, if I may say. Well, so this paper is dedicated for the 80th birthday of Jan Wronski, as you can see here, him. By the way, I was in touch with him, but he told me that he will not attend the talk because he's presently at the hospital. I hope that it's nothing difficult, but that's it. Wronski, he had 80th birthday on 21 September, as it's written here, and this is a photograph of him. So I will say a few words about him because maybe some people don't know him. So it's already good to talk about the people who are working in logic. And first of all, I was invited to write this paper by Andrew Schumann, who is working with Wronski at the University near Krakow. He's working with his journal, Studia Humana, edited in Poland. And at the same time, he edited a special issue of this journal, and also this was published as a book, as you can see here. Everything is published right now. So Wronski had a very prominent role in the development of the knowledge of the school in Poland. Because the Warsaw School, sorry for my English, the Warsaw School was very important, one of the most important schools of logic at any time in the world. So, but since after the war, the Second World War, most of the Poland was destroyed at some point, and was destroyed by the Nazi, and then there was occupation by the Russian. So everything was in some sense forgotten. And Wronski made a lot of works to preserve the history of this school, which was very important during 50 years. So here you can see some books. In fact, he published a lot of papers, books about this school, more here. And the relation between the Warsaw School and the Vienna Circle. I myself participated to one of the latest books about this school, which was published in 2018, and this book was launched in Vichy at the Universal Logic meeting, where Wronski was there and many Polish logicians. So my talk today is related to Alfred Tarski. I think everybody have heard about him. And we managed to create the Alfred Tarski Logic Prize 2 years ago to develop logic. It's part of a big project to develop logic prize in many countries in the world, starting here in Brazil with the prize for Newton da Costa. Also, it's related with another project I've been working on, which is a World Logic Day every January 14. And it's related with the birth of Alfred Tarski, the death of Kurt Gödel, and also the death of Lewis Carroll, which is connected with my talk here. In a few months, in 1 month and a half, we will have the third edition of the third edition of the World Logic Day, 14th of January 2001. You can see the link here. Nowadays, it's managed by this agency, which is related with UNESCO. Okay. So after this general presentation of the perspective of my talk, why I wrote this paper, because André Schumann asked me to write a paper for this special issue of dedicated to Wolanski, and then I say, well, I was thinking about that, and I had a very few days to write the paper, and I say, well, I will write something which is related to the Polish school. Myself, I've been working with Polish people since 30 years. I spent 1 year and a half doing research there many years ago, and I've been there nearly every year. So I know a lot about these people. So I was thinking, and I choose this topic, the logic, the question of the logical notion, because I think it's a very interesting topic, and it's still not so well known. I will explain the situation of this topic is a bit ambiguous. Why it's a bit ambiguous? Because you see, as it is written here, an original idea not to be found in logical textbooks. It's true, you open a textbook on logic and you will not see anything about that. It's very difficult to find something about this logical notion in a presentation of first order logic, in an introduction to first order logic. We can check. But most of the book, introduction to logic, first order logic, because this notion is related to first order logic. Most of the books about first order logic don't say anything about this idea of logical notion. Very difficult to find. At the same time, this paper published after the death of Tarski, it's a very famous paper. But it's famous among people who are doing research. It's not famous among, people, students, and something like that. So it's really something related with with research. So Tarski presented at least 2 talks. This you can see on the slide the 2 famous talks. He presented one in UK and one in USA, but I was talking with different people, and they told me that they attend a different talk at the same time about the same topic. So probably at this time, during this period, probably Tarski, I would say, he gave about 10 talks about this topic. And then he had some notes about these talks. And Corcoran was a good friend of him. He's famous because he is editor of the collection of paper by Tarski, Logic, Mathematics and Semantics. And then John Corcoran, he published this paper after the death of Tarski. But, it's important to say, before Corcoran already wrote the paper before the death of Tarski, and already showed to him this paper. So this paper was approved by Tarski, but it was published for different reasons. As we know, publication is not necessarily easy, only after the death of Tarski. Okay, so now, what are logical notions? What is the main idea of Tarski? In this paper, it's related with this program of Felix Klein, the question of invariance under one-to-one transformation. Sure. So what does it mean? For me, it's very important to present a general idea beyond this this work, and not only in a technical way. And in fact, I must say that what is good in this paper by Tarski, it's not something which is very technical. I mean, it's a paper that can be understood by many different kind of people. Not so easy, so that's why I decided to write this paper, which is even easier to understand that than the proper paper by Tarski, because I think it's very important, and it's to make logic more easy to understand to everybody, and it's not necessarily difficult to do that. So, what is this idea of one-to-one transformation, invariant under one-to-one transformation? Well, it's a question, it's a name that we have from the Greek language, isomorphism. Isomorphism means that we have something which has the same shape. The same shape. Good. What does it mean to have the same shape? Well, same shape, morphe means kind of shape. But this is only one starting point. So you can see all this, we have a different kind of cats, and in some sense, they have the same shapes. Now, the same shape. Now, if you go to another level like animals, you see it's not so easy, because can you say that all these these animals you can see here on this picture have the same shape? Well, but they have something in common. Well, so isomorphism, we want not only to stick to some shape, we want to have something more general, something common among some different kind of objects. Sure. In mathematics, but not only in mathematics. And let me give you two other examples. You see all the cars. So the idea of the cars is interesting because it's not only the question of shape, it's the utility, the use you will do, the use, how you will use this kind of, what is the object, what is the use of this kind of objects. And then also you have another different kind of thing, like all the red objects. In which sense we can say that all the red objects have the same shape, are isomorphic. Well, in which sense they are isomorphic. This question are very important because the idea of Tarski is to say that the logical notion are those invariant under any one-to-one transformation. So we are going at the very abstract level. So logic is something which is beyond all these particularities. That's why I'm giving this different kind of example to see that logic is even more absurd than all this kind of example, because we want to find something which is common to all kind of things, if I may say, without any such kind of specificity. So it's something which is very abstract. And then Tarski in this paper, he explicitly says that this idea is not only his idea, that he developed this idea with Lindenbaum during the time he was in Poland, and that they published the paper about that. You can see the reference here about this idea. So it's an idea of both Lindenbaum and Tarski. Sure. Then this concept of logical notion as one-to-one transformation can be very tricky, can be very formal, can be very mathematical, and it has been discussed by different people. I quote two of them who were working a lot about this subject, Gilles Hacher and Denis Bonnet. Because one of the difficulty if we go at the technical level of logic is, well, one-to-one anyone, I'm going back to here, anyone invariant and any one-to-one transformation, but any one-to-one transformation between what? That's the question, between what? So the idea is, what kind of basic framework we will have to work on. And these two people, they investigated this question. What kind of, exactly what kind of specificities we can give to this one-to-one transformation to have a very general framework, how we can do that, how we can generalize that. But this is not, when I was writing this paper, that it was not my objective to talk about that. My objective was to, on the opposite to that, to start with a very simple approach that I will explain here, to make something very simple, because I think the idea, this idea of Lindenbaum and Tarski can be presented in a very simple way, if we consider the most simple cases, and then we can understand what it means. And after that, of course, it's important to work the details of a more specific situation. So why wanting to make something very simple, very childish? Well, I think there is a tendency to underestimate the intelligence of young children. So it's not so simple. It's not so simple, but at the same time, every child and every human being has the capacity to understand basic things, and things which are really already at a good level of understanding. So I think everybody can do that if we go in a good direction, if we present the thing in a good way. So for me, I'm trying to do that. Now there is a quotation of Grothendieck with one of the most famous mathematicians of the 20th century about the child, not to say that what are the quality of the child, not to have fear to do something wrong, not to be serious, to do something, not to do the same as everybody is doing. I think so it's very important for the development of research. And I think this quotation is interesting because we see that Tarski and Lindenbaum, they had some very original ideas. So I think it's important to have original ideas. How we can do that? That's the question. Huh? We don't necessarily need to follow some line. We really, to have original idea is to really think at the most important level, what are the meaning of the basic concept? In this case, the basic concept of logic. And more comments about that. I think also it's important to try to speak in a very simple way, to try to explain to everybody. There is a famous quotation, which is not here, by Einstein. He said, well, if you can explain something to a 6-year-old child, you cannot. It means that you cannot understand, that you don't understand the thing. So I think it's funny. So if you understand something, you are able to explain to anybody, to any rational animal, any human being, and human beings, they develop their rationality already at a young age. That's my point here to write this paper. And this quotation by Kempis, purity and simplicity are the two wings with which man soars above the earth. So I think it's very important to be able to be simple, because it's by starting to be simple that we can go to the more complex things. Okay, so you will see that we will start with a very simple situation. We start with a very simple situation, which you can see here. It's these 4 logical notions. In the Tarski paper, there is not, you cannot find this diagram. I think diagrams are very useful to understand, to develop the understanding. So you see here these 4 configuration, these 4 presentation of the logical notion. It's very simple, you know. You have two. I'm taking the case where we have only two objects. If we had only one object, it will be trivial. But we have when we start with two objects, we are already in a situation which is not trivial. And then we have two objects, and then we can describe, we can figure, we can imagine these four situations. Certo? Sure. Então, what do we have? Emptiness. There are no relation between any objects. Universality. Every object is related with another object. Identity. The situation with an object is related with itself, and there is nothing else. And difference, it means an object is related with an object which is not identical to him. Then you have this picture. It's very simple. I think everybody can understand that. And these are the four logical notions according to Lindenbaum and Tarski. In the case of the most simple situation. Now, if we want to generalize that to any kind of more complex situation, okay, it's good. It's not necessarily difficult. Generalization is not necessarily a difficult task. Sometimes it's more important to understand the complex problem at the simplest level. I think so. Well, because we'll see that even at this level, which is quite simple, we already have some problems. Let's go. First of all, let's understand the difference between these four situations and an example of something, a non-logical relation. And what does it mean? So a non-logical configuration, for example, is this one. So why it's not logical? Because we can try to describe the situation. So I wrote here a formula in first order of logic without equality, which describes the situation, which is quite easy to understand if someone know a bit about the symbol of modern logic. So there is an X which is not related with itself, as we can see here on the left, and there is a Y which is related to himself. It's related to Y in one direction, not in the other direction. So we can see the relation between this formula and this diagram. So what we can say is that this diagram is a model of this formula. Now another question is the following. So that's one point. Everybody agrees that this formula describes the situation. That's one point. The other point is, well, but maybe this formula is also describing another situation. So, and this is the case, because this formula is also describing this situation. You see, it is describing these two situations. Is this a problem? Not necessarily, because we have this idea of isomorphism, which is fundamental in this approach by Lindenbaum and Tarski, and we can see that these two configurations are isomorphic. These two configurations are isomorphic in the sense that we can make correspondence to objects of these two structures, and this will respect the structure of these two configurations. Okay, so that's not a problem. What is a problem? The reason why this configuration is not logical is because if we go to a situation when we have three objects, because we want to work with any kind of any quantity of objects, then in this case, this formula is valid, is true. This formula is true in two different configurations which are not isomorphic, as you can see here. Because in these two configurations, you have the same basic structure that we had previously, but we just add a third element, which is not in the same, which has a different behavior on the left and the right. Yeah, sure. you can see. So these two configurations, still, there are, as we say, model of this formula, but they are not isomorphic. So that's why this situation here is a non-logical configuration, because we cannot generalize it to any element, to any quantity, to any numbers of elements. If you think about this, you can see easily that you can generalize that. You can generalize this four situation to any numbers of elements. Let's see, emptiness. You put 10,000 elements without nothing. This situation will be simply the same. Universality is the same. Identity is the same. Difference is the same. So in the case of logical notion, if you change the numbers of elements, the configuration is not changing. So all this configuration will always be isomorphic in each cases. In each cases, all the configuration will be isomorphic independent of the numbers of objects, which is not the case here, as I was explaining. So we have three basic questions about this situation. Categoricity means that all model should have the same configuration for one specific cardinality. So categoricity is a necessary condition for logicality. Can we say that it's a sufficient condition that if a formula is categorical for each cardinality, does psi describe a logical notion? Second question, if a binary relation can be described by a categorical formula, is it sufficient to consider to be a logical notion? These two questions have a positive answer because it's the basic idea of Tarski-Lindenbaum logical notion. So it's easy to reply. Now the third question, and this is a problematic question, is a binary relation considered to be a logical notion only if it can be described by a categorical formula? And we will see that it's not the case, not necessarily the case. So that's the most difficult question. Okay. And to answer this question, the third question, we have to examine the situation of the expression formulas, how we can express this different situation. So we see now we can describe these four logical notions: emptiness, universality, identity, difference, using a formulation in natural language. Emptiness, nobody is in relation with anybody. Universality, everybody is in relation with everybody. Sure. Identity, everybody is in relation only with himself. A difference, everybody is in relation with everybody except with himself. So these are simple formulation, and it's also simple to express this in natural language. But then we have a problem with the expression of these ideas in first-order logic without equality. And that's one of the difficulty of modern logic, because we are using some kind of formal language, and we have to check, we have to be aware and to see if it's working good, in the sense, do we have a good correspondence between these formulas of first-order logic? It's not only because we have some symbols and something like that, but exactly what is the meaning of these formulas and the idea beyond these formulas. So the formulas, it's not just a transcription, it's not just like an abbreviation. These formulas in first-order logic, they change our way to express and to think. And that's why this question is very interesting here, because we can see that in fact the situation in first order logic is not so easy, because we cannot express, we cannot formulate identity and difference in first order logic. It's something very surprising, and which is not until now, which is not so well known. Some people, some other things are most well known, that you cannot express many different complicated concepts in first-order logic. But how is it possible to explain that to a notion which is so simple as identity? We cannot write a formula which expresses this idea. That's the case. There is a theorem proving it's not possible. And, and obviously, it's the same for difference, because one is a negation of the other. So we have this very surprising result that we cannot express identity in first-order logic without equality. Now people say, well, but we have an idea of equality, identity. There is these two words for this notion, identity, equality. So there is a Leibniz formula saying that two objects are identical if they obey the same formulas. And this symbol was the symbol of equality was introduced by Robert Rickroth. But as you can see in this diagram, we can see in a very simple example that here B and C are identical according to Leibniz formula, although they are not identical in the reality of this structure. They are identical according to Leibniz formula because they have the same relation with other objects. Yeah. So this Leibniz identity does not correspond to the identity that we were talking about, this logical identity. It's another kind of identity. It's a congruence relation, but it's not identity in the sense of this simple. Let me come back to this. It's not identity in the sense of this diagram. No, it's not that. Because this B and C here are identical. Okay, now let's go to a further part of this talk, which is the relation between these four kind of logical notion. So since I'm working on the square of oppositions, which is a very central concept of logic, and I think it's a very interesting concept of logic, which was developed by Aristotle itself, and then by Apuleius and Boëtius. I was thinking, well, we have four logical notions. Can we make a square? Can we make a square of this logical notion? What are exactly the relation between this logical notion? What is the configuration? So here you see on the left, a square, the classical square of opposition, the most famous square of opposition with the quantifiers, and then in blue. And you have the notion of contrariety, in green, the notion of subcontrariety, in red, the notion of contradictory, which can be described using some set theoretical concepts, as you can see on the right. So blue, this blue notion of contrariety means mutual exclusion. The green situation, subcontrariety, means full intersecting union, that you may have an intersection, but you have to complete everything. And then complementation is classical negation. You have separation, a dichotomy. So if we look at these four logical notions described by this kind of Robinson diagram that you can see on this table, then we can easily see that we have this red cross of contradiction between these four notions. But then we have this relation. But then if we go to if we want to have a square, if we want to understand what are the relation between these four elements, we will not have a square of opposition in the classical sense, because you will see that we will have subcontrariety at the top, on the left, and then we have contrariety on the right and at the bottom. So it's a specific case which is completely different from the difference of the quantifier. interesting because I think when we want to understand something, that's why I think square proposition is interesting, because when we want to understand something, the square is not only about quantifiers, it's also about logical notion like possibility and many other notions. When we want to understand something, it's a good way to understand something is to establish relation with different concepts. So the square proposition is a very nice structure to have a better understanding about all that. That's why I was trying to apply the square proposition to these 4 basic notions. And we see that we have this strange situation here. Okay, now let's go to the last part of my talk, which is called the logicality of variety. So the idea of logicality of variety is to consider all notions which are not logical notions. So in the case of binary relation between 2 elements, we have 16 cases. We have 16 configurations. So 4 are logical notion, and then the 12 other notion are not logical notion. I call them variety because they are various by opposition as logical, which is something regular. And here is a description of these 12 cases of notion which are not logical. The remaining cases of configuration, if we left out the situation, the logical notion. And you can see it's interesting that in fact we have 6 notion, 6 configuration which are similar to other 6 in the sense that they are reverse one of two, so they are isomorphic. So in fact, when we are talking about 12 situations, by isomorphism we have only 6 situations because they are isomorphic 2 by 2. Very good. But as you can see, so they are isomorphic 2 by 2, but if you take different ones, you can see that among these 6 situations, you have non-isomorphic structure like that. Okay. So now the enigma. What is the enigma? The enigma is how we can we characterize this 12 situation. If we go to another cardinality, I mean, if we go to a structure with 3 elements, it will not be 12. There will be more. The idea is, can we find a formula which characterizes this situation to be non-logical? Can we have a formula which characterizes all the configurations which are non-logical? That's my question about this paper. That's the main enigma of this paper. So, do we have a first order formula without equality whose model are exactly the variety of non-logical relation for any cardinality? Well, so you can see non-emptiness. You can write for every cases. It's easy for every case. You can write a formula. Identity, you cannot write a formula for identity, but you can write a formula for a non-identity. As I was explaining before, let's come back here. You see these 2 lines here at the bottom. We don't have a formula for that, for identity for difference. We don't have a formula for that in first order logic. Now, if we go to here, if we go to non-identity, well, we can write a formula. There is an X which is not in relation with him. No difference. There is a formula which is in relation with. So it's at first you say, well, maybe it will be easy because we can find for each of these cases, for each of these negation, of this logical notion, for each negation of this logical notion, well, you can find a formula. You see, non-emptiness, non-universality, non-identity, non-difference. You have a formula for each of these cases. So why not putting all this by a conjunction and say, well, by this conjunction, we have the solution. Why not? But this doesn't work because we have here, for example, we have among these 12 configurations, among the 12 configurations of non-logical notion, we have four of them which obey this formula, as you can check. So we have 4 of them that do not obey this formula. So this formula does not work for characterizing non-logical relation. So I wrote this paper. My paper was ending at this point, and then I wrote the paper in a very short time because this was a special issue and I have to send the paper and something. I wrote the paper maybe something like in 2 weeks. But after I wrote the paper, I decided to, since I didn't know the answer to this question, so I decided to ask, since the problem was clearly presented, I decided to circulate the paper to see what would be the reply if someone has an idea of this to this question. And what can I say? I mean, many people, as we know, everybody is busy. So many people say, well, it's interesting, but I don't have the time to think about that. Some people say, well, for me, I don't know the problem. I cannot find a solution. And but some people gave me some replies. So I was making this offer not to go to the bull crater because I'm promoting this organization of logic, Logical Universalist Association, which is in Portuguese it means the moon, Lua. Okay, and we know that there is a crater of bull on the moon. Okay, so I was asking people, well, if you find an answer to this enigma, we will offer you a trip to the moon. So I don't know if it was very attractive to make this offer, but anyway, I received some replies. I will give you an example of a replies which does not work, but which is interesting in some sense. This is you see this formula here on the left, and this formula on the left, this formula, it characterizes exactly the 12 case of non-logical notion for a situation when we have 2 elements. So this situation is a reply. It's a reply for the case of a 2-element situation. But it does not work if we have 3 elements, as we can see here. If we can see here, because this configuration is a model of this formula. Sure, this formula. And so that's why it's not a good answer to this question. Now, I must say that I receive mainly, I received about 5 replies, which are more or less interesting. And among these 4 replies, I received 2 of them, which are, I think, a good answer to the question. And these 2 answers to the question, they gave a negative answer to the enigma, that it's not possible to find a formula which characterizes the non-logical relation, not possible. But the answer to these 2 answers to this question are completely different from each other. And in the future, I have the intention to write a paper presenting this solution, explaining why they are good and why one is better than the other one. Not only these two ones, I will also comment on other more answer I received, and that will be it. Now, if some people still want to, if some people still want to send an answer, I'm not presenting the answer here today in this talk. That's not my objective. So if some people after this talk still want to present a solution to this enigma, it will be nice. Okay, so I will conclude here. Thank you very much.